Hello, today we'll be learning about MIPS assembly language, different instructions supported in the MIPS processor, and also set of instruction, I'd say a pseudo instruction in the MIPS processor. So this note is mainly coming from the appendix A of your textbook, Patterson's book. So basically, who doesn't have that book? I already got that pages for you from that book for your reference. So to start with, before even we dive down into the different MIPS instruction, let's see what are the different addressing mode in the MIPS. So addressing modes are basically it describes how one can access operands from the processor, inside the processor, or from the memory. It's all about how we are going to access the operands and stuff like that. The very first addressing mode for MIPS is this register addressing. So in this type of addressing, the operands are the registers. Okay, so to access operands either for loading the value or storing the value to and from the operands, you use a register as that storage. For example, if we see that li pseudo instruction, we have seen it before, like this, right? Li, let's say T0 0xA5, right? So here, see this guy, what it is doing, it is actually putting the A5 value into T0, right? So load immediate value to this T0. So here T0 is acting as an operand which is a register accessed. So for this li instruction, this operand, the target storage, is a register. So this is a register addressing mode. All right. Now there is another mode called this base or displacement addressing. Now what is that? That's basically, it's an operand, is a memory location whose address is the sum of a register and a constant in the instruction. So we'll learn about those instructions in maybe this lecture, or maybe in the next lecture, right? And I think before that also, in the memory discussion, we have seen some part or at least some form of this displacement addressing. So what does it mean really is this, like I have an operand, so I want to access operands from memory location. Okay, let's say that operand be O, and this address of O is determined by the content of a register. For example, let's say register S0. So the content of the register S0 plus some immediate number given in the field. So that means essentially this type of displacement addressing is involved I type of instruction. If we recall, the different type of instruction is I type of instruction, because one part of the instruction is the immediate. Okay, let's say S0, the content of the S0 was something like this: 0 1001 0000 Okay, and my immediate was passed as let's say 0 cross, that is a 16-bit. Of course, this is 16-bit. We all know that for MIPS, immediate is 16-bit. So maybe 00 0C. Okay, so what is my address of the O in that case? Address of O, that operand, would be this guy, essentially this one plus this one, right? Which is essentially is, if I just bring out the calculator and in the hex mode, if I see, okay, 1001 000C plus 000C, or yeah, so it's become your, so the operand address is essentially become like this, right? 0, of course, it's a hex number, so it's become like, so in this operation, that particular operand O will be accessed from this memory location, which was determined by the content of one of the register and some offset, if we can think in that way, an offset from that address. Okay, so that is why it is called a base or displacement addressing. All right. Now, next one is your immediate addressing. Okay, immediate address we kind of familiar with already. We know the I-type instructions. They are basically the operand is a constant within that instruction itself, and it's an, in other words, like we are supplying the value to be operated on, right? So it may be one operand, maybe a register, and maybe the target storage may be in register or memory, but another operand is an immediate number we are directly embedding in the machine code of the instruction. Okay, so that's the immediate addressing. Now the PC relative addressing, the next one, is a little bit interesting. So this is more like related to jumping from a point in the program to another location, like the go-to or branch, test and branch kind of operation. So this is basically relative. It is similar to this base or displacement addressing, but the register we are using here is strictly the PC. So it is relative to the current content of the PC or program counter, and a constant which is an immediate in the instruction field. Together they sum it up, and then it basically do the relative addressing with respect to the PC. Now this part poses a very interesting observation. So my next address, so here what I'm telling is that my next address is a PC relative immediate, right? Now immediate is 16-bit sign number, right? And we, in most of the system, it is in a 2's complement form. Okay, so that means my immediate range is from, it would be like 2 minus 2 to the power 16. So basically it's minus 2 to the power 6 16 bit, right? So it will be minus this one to plus this one, right? Something like that. Minus 1, something like that, right? So let's see, let's approach it in another way. So 16-bit means total it can address 2 to the power 16 different numbers, which is 2 to the power 6k location. 2 to the power 10 is 1k, which is like 8, 16, 32, 64k. 64k. Right. Now, since it is a signed number, so the range is basically minus 32k to 32k. Okay, so minus plus. So that means, which means I can, from a relative to a PC, I can jump forward 12k, like sorry, 32k location max, and I can jump backward 32k. So from the PC location, I cannot jump really long. Okay, but so really I cannot jump to the arbitrary location, arbitrarily distant location from the current code. So we are bounded in this addressing mode. We are bounded by this 32k value. Okay, which is coming out from this 16-bit signed number limitation. Okay, 16-bit can represent 64k. So plus and minus in both range, it will be minus 32k to plus 32k. So from with respect to the PC, I can either jump forward till 32k location and jump back 32k location. But most of the cases, this is okay, right? We don't want to have very long jump in a program. Long jump has its own problem itself. So usually, like when we do a program like this and assembler assembles your program, your assembly program, it try to put everything within 32k. Try to put. Okay. So that is the one interesting property of this PC relative addressing. The other addressing is called a pseudo addressing. So now the jump address is basically 26 bit of the instruction concatenated with the upper bits of PC. Okay, so for example, let's say jump J some level, like level 1, or let's say, okay, loop 1. Okay, now we know the jump instruction is basically your opcode is like 6-bit opcode, 6-bit opcode, and followed by 26-bit of address. Right. Now the target address, so where to jump, right? So what is the number I'm going to do? So basically, whatever the PC value is like 32 bit. So I have like upper 6-bit value. Let's say this is like B, and or let's mark it as a U, and followed by 26-bit of lower bits. Okay. Now let's mark this as a 26-bit of A. Now my next address is basically U followed by A. Okay, U followed by A. So that is a pseudo direct addressing. So it is not a direct addressing that we are picking up the 26-bit of address and jumping to that, but it's kind of we are taking a part of the PC, and then that current value of PC, that upper 6-bit, is concatenated with this 26-bit of address and to construct my next address. Okay, so this is a concatenation. So don't just mix up with an OR operation here. This is not an OR operation. I'm just trying to show you the bit separation or partition, like 6-bit opcode partition with 26-bit of address for this instruction format JLoop, and then my PC is also partitioned into upper 6-bit and lower 26 bits. And what is my next address? It is consists of the PC's upper 6-bit and the instructions lower 26-bit, which is A. All right.